Okay, welcome back. For the final talk today, we have Edward Witten from the Institute for Advanced Study, who will tell us about algebras and entropies for black holes.
So like several previous speakers, I'd like to begin by thanking the organizers for organizing this very nice conference and also for inviting me to give the talk. I'll be talking mostly about this paper here, Gravity and the Cross Product. There's a more recent paper that extends the analysis or makes a somewhat similar analysis for de Sitter space. But for one talk, I will just talk about the black hole. But I'll start with a motivating example from affine Lie algebras, which might be more familiar to some of you. An affine Lie algebra is a central extension of the Lie algebra of maps from a circle to an ordinary Lie algebra, usually taken to be simple or semi-simple. Then, if H is a representation of an affine Lie algebra, then there's what physicists call a current, and you could smear it with any function on the circle valued in the Lie algebra to make an operator, J of F. And bounded functions of these operators would generate the type 1 von Neumann algebra of all bounded operators on this Hilbert space. But you could divide the circle into two pieces, A and B, and consider only functions with support in one region, say region A. Then operators J of F generate what's called a von Neumann algebra of type 3. That notion might not be familiar, and I'll explain enough later to make this talk understandable. Well, the fact that if you consider only part of the circle, you get an algebra of type 3 is a special case of something more general. It holds for any quantum field theory in any dimension. Suppose we're in D space-time dimensions, and therefore in little d equals capital D minus 1 space dimensions. Well, there's a Hilbert space H, and if we consider all quantum fields throughout space, they generate a type 1 von Neumann algebra of all bounded operators on H. But if we divide space into two disjoint regions A and B, as shown in the picture, and consider only operators in region A, we get an algebra of type 3. This is a result originally due to Araki in the 1960s. Well, as a physicist, why would one care about this? The basic motivation comes from black holes. In the application to black holes, region A would be the region of space that's outside the horizon, in other words, causally accessible to an outside observer. Region B is the interior of the black hole, the region behind the horizon. Thus, the operators available to us if we live outside the black hole horizon are the operators in region A. And as I've just explained, in ordinary quantum field theory, this is a type 3 algebra. However, gravity doesn't fit into the framework of ordinary quantum field theory. Trying to modify the framework of ordinary quantum field theory so that gravity would fit is the main goal of string theory. The main point I want to convey today is that there are reasons to believe that when gravity is taken into account, the operators outside the black hole horizon are no longer an algebra of type 3, rather they're an algebra of type 2. This is when gravity is taken into account for very weak coupling. Newton's constant is very small. It's just even treated perturbatively. So for infinitesimal gravity, the type 3 algebra becomes a type 2 algebra. And this helps resolve some issues about quantum black holes. Again, I'll have to say a little about what is a type 2 algebra. But before that, we have to review the idea of black hole thermodynamics, which is by now about 50 years old. Roughly, by coincidence, it was invented in more or less the early days of string theory. Jacob Bekenstein, inspired by questions from his advisor, John Wheeler, asked what the second law of thermodynamics means in the presence of a black hole. For an ordinary system, the second law says that entropy can only increase. But if we toss a cup of tea into a black hole, the entropy seems to disappear. Bekenstein wanted to generalize the concept of entropy so that the second law would hold even in the presence of a black hole. So by way of analogy, think about energy rather than entropy, which might be more familiar. According to Newton's laws, energy is conserved. And as physics advanced, conservation of energy was kept. But in order to keep it, the concept of energy had to be generalized. So for example, it was understood that heat is a form of energy. And then it was understood that rest mass is a form of energy, E equals mc squared. And gravity refines what one means by energy as well. So energy remained an important concept as physics developed, but it had to be generalized. So Bekenstein's idea was that similarly, the second law would be universal, but to make it universal, he would have to generalize the notion of entropy. So he wanted to assign an entropy to the black hole. So he needed a property of a black hole that can only increase. It's actually not true that the mass of a black hole can only increase. If you have a spinning black hole, you can slow down its spin by sending in counter-rotating matter. And it's possible, as originally shown by Penrose, to slow down a black hole spin and thereby reduce its mass and extract energy from the black hole. And it's even believed that that happens naturally in galaxies that are producing enormous jets of energy. It's not true the mass can only increase, but at the time Bekenstein was working, Stephen Hawking had just proved the area theorem that says that in classical gravity, the area of a black hole horizon can only increase. So it was fairly natural for Bekenstein to propose that the area A of the black hole horizon should in some sense be a contribution to the entropy. Well, to be more exact, since entropy is dimensionless, but A, of course, has dimensions of area, or length squared if we're in 3 space dimensions. To make it dimensionless, Bekenstein proposed that a multiple of the area over Newton's constant times h bar should be viewed as a contribution to the entropy. And Stephen Hawking, in his most famous work, later showed that this is correct, and the coefficient is 1/4. So Bekenstein proposed that the real second law is not the traditional one, but that the quantity that really obeys the second law is a generalized entropy, which is the sum of S out. S out is the ordinary entropy of matter and radiation outside the black hole, plus the area over 4g h bar. The idea is that this is the correct entropy to which the second law applies. When we toss a cup of tea into a black hole, S out goes down, but A over 4g h bar goes up by more. Supposedly, Stephen Hawking was trying to disprove this, but ended up proving it. I don't really have time today to sketch his analysis, but it had to do with looking at the behavior of quantum fields interacting with the black hole, for which I've drawn a Penrose diagram here, but I won't explain what the picture is. Now, for an ordinary system, the entropy measures the number of degrees of freedom, or more precisely, the number of degrees of freedom that are relevant under a given physical condition, which usually means a given temperature. So many researchers have thought that somehow the entropy A over 4g of the black hole horizon means that the black hole horizon can be described by some sort of degrees of freedom that live on its surface with sort of a unit degree of freedom for every 4g of area. For example, in a famous article in 1992, John Wheeler illustrated this idea with a picture I've copied here. He visualized the black hole horizon drawn in little cells of area 4g, and he imagined a bit or qubit in each cell. As I said, the article was published in 1992, 20 years after Bekenstein's work. Wheeler had been Bekenstein's advisor, and I wouldn't be surprised if he'd been drawing this picture for 20 years. Now, black hole thermodynamics has been spectacularly successful, but unfortunately, it would be a different lecture from the one I'm giving today to try to explain that. But it turns out that subtle properties of classical general relativity work out in such a way that the generalized entropy does behave like a thermodynamic entropy. For example, I already mentioned one aspect, which is the Hawking area theorem that motivated Bekenstein. And that motivated Bekenstein to postulate the generalized second law. The most complete proof of the generalized second law was by Aaron Wall, and makes use of Tomita Takasaki theory of von Neumann algebras. And other subtle properties of classical general relativity work out in such a way that the first law of thermodynamics is also satisfied. So anyway, there's a quite amazing story where classical and semi-classical gravity match nicely with the thermodynamic interpretation that started with Bekenstein's work. And there's much more besides. There's abundant evidence that that the generalized entropy really is an entropy. But is it an entropy of something? That's been a mystery since the early days of black hole thermodynamics. In today's talk, I'll explain a slightly abstract answer. With gravity taken into account, the operators outside a black hole horizon form a type 2 algebra, and generalized entropy is simply the entropy of a state of this algebra. I want to pause for a moment to explain something about entropy in quantum mechanics. When we're making an observation or analyzing an experiment, we're usually studying not the whole universe, but a small piece of it. Maybe the experimental apparatus if we're in a lab, or maybe if we're doing astronomy, the Milky Way galaxy. But anyway, we aren't usually studying the whole universe. Let me refer generically to what we are studying as A and refer to the rest of the universe as B. So the combined system AB is the whole universe. Usually in quantum mechanics, we can assume that the subsystems A and B have separate Hilbert spaces, HA and HB. Then the Hilbert space of the combined system is a tensor product. HAB is HA tensor HB. In such a situation, we can define an algebra curly A of operators in system A. They're simply operators on HA. And similarly, an operator curly B for the system B, they're operators on HB. And these are by definition type 1 von Neumann algebras. Type 1 von Neumann algebra is just the algebra of all bounded operators on a Hilbert space, here HA or HB. Now, the property of a type 1 algebra that we'll use is that there's a non-degenerate bilinear form on the algebra given by the trace in the Hilbert space of AA prime. Suppose we now consider any state of the whole universe. For simplicity, we'll take a pure state. So by a state, I will mean simply a vector in the Hilbert space of the universe. We want to define the entropy of system A when the whole universe is in the state psi. We consider the linear function on the algebra of observables of system A that takes an operator to its excitation value in the state psi. Remembering that the algebra A has a non-degenerate bilinear form, we see that the function f of A is the trace of A times rho for some unique rho in the algebra. It's not hard to show that rho is self-adjoint and non-negative. Moreover, if psi is a unit vector, meaning that its norm is 1, then the trace of rho, which is the trace of 1 times rho, as a special case of this formula, is the same as the excitation value of 1 in the state psi, and that's equal to 1. So rho has trace 1 as well as being self-adjoint and non-negative. An operator with those properties is called a density matrix. So we've learned that any state psi of the whole universe determines a density matrix for the subsystem A. Conversely, if rho is a density matrix, it's not hard to show that it's the density matrix of some psi, assuming that system B is big enough. When a system A is described by a density matrix, its entropy is defined to be minus the trace of rho log rho. That formula is due to von Neumann, and it's called the von Neumann entropy. The way he invented it was that he chose the function rho log rho so as to agree in the classical limit with the classical formula for entropy due to Gibbs. It's not hard to prove that S of rho is 0 if and only if rho has rank 1, otherwise it's positive. Now, when thermodynamics is valid, the von Neumann entropy is equivalent to thermodynamic entropy, but it's defined universally for any state, as we have seen from this formula, which clearly makes sense for any density matrix. Now, forgetting where it came from, if you just have a density matrix rho, the function trace of A rho is a linear function of the algebra that's positive in the sense that f of A dagger A is positive for any, or non-negative at least, for any A. A function with those properties defines what's called a state of the algebra A. The state is called pure if it's not a convex linear combination of other states. It's not hard to prove that rho is a pure state by that definition if and only if it has rank 1, or equivalently entropy 0. So pure states have entropy 0, and mixed states, which are states that are not pure, have positive entropy. Now, if rho is a state of a system A that arises as a density matrix of a vector that describes the state of the whole universe, it's not hard to prove that rho is a pure state of system A if and only if the vector is a tensor product. So if psi happens to be the tensor product of a vector in HA with a vector in HB, then rho has rank 1 and entropy 0. Psi is called a product state. So system A has 0 entropy if and only if the state of the whole universe is the product of a state of system A and a state of the rest of the universe. That's possible, but highly atypical. Now, the idea of interpreting the Bekenstein-Hawking entropy as von Neumann entropy goes back to Raphael Sorkin in 1983. His idea was the following. In a quantum field theory, divide space into two regions, A and B. In his application, B is the region behind the horizon, A is the region outside the horizon of a black hole. But for the moment, consider any two regions. Let psi be a state of the whole universe and rho the corresponding density matrix for the algebra A of operators in region A. That's a naive formulation, and we'll have to be more careful later. Then he tried to calculate the entropy minus trace rho log rho. He found it was infinite. It's ultraviolet divergent regardless of the state psi, and the coefficient of the leading divergence is proportional to the area A of the boundary between regions A and B. That happens because the divergence comes from high energy or short wavelength modes that are localized near the boundary. So modes could be localized near any point on the boundary, so the divergence is proportional to the area of the boundary. Well, instead of throwing this away because it was divergent, Sorkin published it, suggesting in modern language that somehow gravity would cut off the divergence, leaving an entanglement entropy in the vacuum that would be still proportional to the area, but with a finite coefficient. He imagined a coefficient 1/4g to agree with Bekenstein and Hawking. And if that's the correct answer, then if g is 0, which was sort of the case in his calculation here, he had ignored gravity here since he didn't know how to take it into account, and he got infinity. Infinity, well, if the right answer is that the coefficient of the area is 1/4g, and you try to set g equals 0, then you should get infinity. So that was how he interpreted his answer. So the suggestion that gravity would somehow cut this off makes some intuitive sense because it matches two ideas. One is that A/4g is the entropy of the system for someone who only has access to the region outside the horizon. That's an interpretation of Bekenstein's idea about black hole entropy. And the second is that the divergence is proportional to the area because it comes from short wavelength modes near the horizon, as if after cutting off the divergence, there's a density of quantum degrees of freedom on the horizon that's 4g, as in Wheeler's picture. Susskind and Uglum, a decade later, made a simple observation that supports this point of view. If we interpret S out as von Neumann entropy, so to Bekenstein, S out had been thermodynamic entropy. And that means that Bekenstein's discussion was not universally valid because thermodynamics doesn't always apply. Thermodynamics applies for many particles close to thermal equilibrium. If you have a few atoms, you can't make sense of entropy thermodynamically. But if you interpret S out as von Neumann entropy, then first of all, the generalized entropy is universally defined. But very importantly, Susskind and Uglum showed that the sum of the two terms on the right-hand side is better defined than either term is separately. Sorkin had showed that the second term is problematical, ultraviolet divergent. But there's actually a more elementary fact that wasn't pointed out in this context before Susskind and Uglum, that the first term has the same problem because there's an ultraviolet divergence in the relation between the bare Newton constant G0 and the physical observed Newton constant G. In one loop order, the relation is what I've drawn here. And with a constant C and lambda and ultraviolet cutoff, Susskind and Uglum argued that the ultraviolet divergence in 1 over G cancels the ultraviolet divergence in S out. And that's been borne out by later work. So following Susskind and Uglum, we know that the well-defined quantity is really the generalized entropy. And 21st century developments have strongly supported this point of view, though leaving plenty of mysteries. And in the limited time today, I'm afraid I may have been rushing a little bit too much because I didn't want to have at least time to explain one point, but because of the limited time, I'll only talk about one aspect of the story. Why is it that the entropy of the region outside the horizon is ill-defined in quantum field theory, so that S out has that quadratic divergence that Sorkin pointed out, but well-defined once gravity is included? I'll give, as I said at the beginning, a somewhat abstract answer to that question. First of all, as already explained, in ordinary quantum mechanics, when we consider a system AB made from subsystems A and B, we usually assume at the start that each system has its own Hilbert space, HA or HB. Then, if the combined system is in a state psi equals psi AB, the density matrix rho of system A generically has a high rank and a positive entropy. But rho might, with the accent on might, if psi is a product state, be a pure state density matrix with zero entropy. Thus, in ordinary quantum mechanics, whether a subsystem A of a larger system AB has a positive entropy or not depends on the state. Generically, subsystem A has positive entropy, but for a product state, the entropy vanishes. That's not the situation for the entropy of a region of space in quantum field theory. The divergence found by Sorkin is an ultraviolet divergence. So it does not depend on the state, or at least the leading ultraviolet divergence does not depend on the state. Every state looks like the vacuum at short distances, so every state has the same leading divergence of the entanglement entropy. So in quantum field theory, it's not true that the entropy is a property of the state, or not only a property of the state. The root of the problem is that it's not true in ordinary quantum field theory that there are separate Hilbert spaces, HA and HB, for the outside and inside regions. There's only a combined Hilbert space curly H for the whole system. What the separate regions A and B have are not Hilbert spaces HA and HB, but only algebras of observables curly A and curly B. These algebras act on the Hilbert space of the whole system, so they can be defined to be Binorman algebras. Binorman algebra is just an algebra of bounded operators in Hilbert space that's closed under weak limits, a natural type of limit. So the fact that ultimately the fact that entanglement entropy is divergent in quantum field theory is because the assumption of separate Hilbert spaces for the two regions is false. Instead, there only are separate algebras for the two regions. Well, we're going to need to know just a little bit about von Neumann algebras. There are three types. A type 1 algebra is the algebra of all operators on a Hilbert space. In ordinary quantum mechanics, when we discuss a system A, it has a Hilbert space HA, and the algebra of observables is the algebra of all bounded operators on HA. One can define density matrices and entropies for a system that has such an algebra, and there are pure states that have zero entropy. So that's the situation we usually assume in quantum mechanics. The other types of von Neumann algebra may be less familiar, and I'll give a brief introduction to what they are, but first the bottom line. A type 2 algebra does not have pure states, but there is a notion of a density matrix or an entropy for a system in which the algebra of observables is of type 2. A type 3 algebra instead is the worst type. The system whose observables form a type 3 algebra does not have pure states and also does not have density matrices or entropies. By now, you may anticipate the bad news. In quantum field theory, the algebra of observables of a region is always of type 3. So to a region, we can never associate a pure state or a density matrix or entropy. The type 3 nature of the algebra is the reason for the universal ultraviolet divergence of the entanglement entropy. Or at least it's one way to explain why there is this ultraviolet divergence. However, it turns out that including gravity, even just semi-classically, changes the picture. The algebra changes from type 3 to type 2. So when gravity is turned on, the region outside the black hole horizon is described by an algebra in which the notion of entropy is well defined, though there's no notion of a quantum mechanical microstate, which would be a pure state of the algebra. We can interpret that as a somewhat abstract answer to the question of why including gravity suddenly enabled us to convert the ill-defined S out into the better defined generalized entropy. But finally, I need to tell you something about Binorman algebras of type 2 and type 3. A type 2 algebra was originally constructed by Murray and von Neumann in exactly the way I'm about to describe it. A qubit is just a quantum system described by a two-dimensional Hilbert space. Let A and B be systems that each consist of countably many qubits, countably infinite number of qubits, but we'll start with just n qubits, where n is a large integer. Then we'll take the limit as n goes to infinity. Keeping only n qubits of system A and n more of system B, I've written a particular state of the system where where each of the n qubits is in this maximally entangled state, where in physics language, the nth qubit of system A could be up or down, or in the state 1 or 2. And whether it's up or down, the nth qubit of system B is exactly the same. And then I divide by the square root of 2 for each qubit, making 2 to the n over 2 in all, to normalize the state. So what I've indicated here is a maximum entropy state in which the n qubits of system A are maximally entangled with the n qubits of system B. And the von Neumann entropy is n, assuming we take the logarithm in base 2. Well, let A and A prime be operators that only act on maybe the first k qubits of system A, where k is no bigger than n. And then we define a function f of A, which is the expectation value of A in the state psi. The definition has been chosen so that as long as in the definition of psi we consider all the qubits that little a does act on, this function does not depend on what other qubits we include in the definition. So n could be much bigger than k, and the precise value of n doesn't matter. As long as the operator little a only acts on k qubits of system A, and as long as we include all those in the definition of the state, f of A doesn't depend on what other qubits there are. The state psi was constructed so its density matrix is a multiple of the identity, 2 to the minus n times the identity. So f of A is actually the trace of A times the density matrix, or 2 to the minus n times the trace of A. From which you can see that f of 1 is 1, and that f of A prime is f of A prime A, because they're both multiples of the trace of A prime. Well, as I said, for any given A, f of A is defined and independent of n as soon as n is big enough. So f of A has a large n limit. It has a limit for an infinite system. So taking the limit of the infinite system, we have defined the function f of A for any operator A that only acts on a finite set of qubits in system A. And of course, it still satisfies these conditions, and it's also positive in this sense. So far, we've defined it on the whole algebra A naught of all operators that act on only finitely many qubits of system A. But now we can take what are called weak limits and complete A naught to a Binorman algebra still with a function f of a with the same properties I've stated. Since f of a prime equals f of a prime a, this function is usually called a trace. We formally write it as f of a equals trace a, but trace a is not the trace of a in any Hilbert space representation of the algebra. The usual way physicists would say it is that this is a renormalized trace with an infinite factor 2 to the minus n removed, where we took n to infinity. So we've constructed a von Neumann algebra on which every element has a trace, and in particular, the trace of the identity is 1. There's a much more elementary example of an infinite dimensional algebra with a trace, the type 1 algebra B of all operators on an infinite dimensional separable Hilbert space H. But in that example, though we can define a trace on elements of B, it's not defined for all elements, only those that are trace class. For example, the identity element of B does not have a trace unless you want to allow infinity as a value of the trace. By contrast, from the infinite system of qubits, we constructed an algebra A in which every element has a trace. So clearly, it's an essentially new kind of algebra. It's the simplest example of a type 2 algebra. It's the type 2 factor of Murray and von Neumann. Small generalizations lead to algebras of type 3. For example, if instead of, if I replace the state we used before by this one, where the nth qubit of system A is entangled with the nth qubit of system B with an invertible density matrix, but not one with not maximally mixed. Anyway, with a slight change in the state, we would get a type 3 algebra. We can do everything we did before, but it's no longer true that f of a prime equals f of a prime a. And then, when we take the large n limit, we instead get a von Neumann algebra of type 3. Algebras of type 2 or type 3 don't have an irreducible representation in a Hilbert space. Whenever such an algebra acts on a Hilbert space, it always commutes with another algebra that's also of the same type, type 2 or type 3. For example, we constructed our type 2 and type 3 algebras as algebras of operators on the A part of a bipartite system, AB. So in that construction, they commute with an identical algebra that acts on system B. The difference between type 2 and type 3, or at least the difference that's important for today, is that a type 2 algebra has a trace and a type 3 algebra does not. Moreover, in a type 2 algebra, the trace is non-degenerate. So if f of a is any linear function on the algebra, it's the trace of a times a prime for some unique a prime in the algebra. So let's go back to the situation first considered by Sorkin. We consider some state psi of the whole universe. Suppose it were true that the physics in region A is described by a type 2 algebra, curly A. Then the linear function that takes A to its expectation value in the state psi would be the trace of A times rho sub A for some rho A in the algebra. That's the condition that in ordinary quantum mechanics for a type 1 algebra we use to define the density matrix of the state psi for measurements in region A. So it makes sense to call rho sub A the density matrix also in the type 2 case. Once we have density matrices, we can define entropies as well. So if the region outside the horizon is described by a type 2 algebra, then we can define an entropy for this region. Well, as I've already explained, in ordinary quantum field theory, the algebras are type 3. But it turns out that when we include gravity, things are different. Gravitational effects, even for very weak coupling, convert the type 3 algebras into type 2 algebras. The mathematical mechanism leading to this for both the black hole and also for de Sitter space, although I haven't prepared slides about de Sitter space, is quite simple, and it was developed by Kahn and Takasaki by coincidence in the same period that both black hole thermodynamics and string theory were getting started. What's new is only that this mechanism was actually implemented by gravity in the field of a black hole. The details are different in the two cases of the black hole and de Sitter space, and I really only have time for a very brief explanation. Although, unfortunately, I've rushed a little bit in getting to this point, so I would have had a little bit more time. Well, before I tell you what happens for the black hole, though, I want to say a word about what on earth Kahn and Takasaki were doing. Their motivation was that type 3 algebras are difficult to study. So they found a simple operation that turns a type 3 algebra into a type 2 algebra. And from their point of view, that was useful because it gave a powerful tool to study the type 3 algebra. Now, it happens that their simple construction that went from a type 3 algebra to a type 2 algebra is exactly what gravity does for very weak coupling. Well, I guess I'll first say what was their definition. So let A be a von Neumann algebra that acts on the Hilbert space H with what's called a cyclic separating vector. So in quantum field theory, the vacuum of the whole universe would have to have the property of being cyclic and separating. It's a technical term in von Neumann algebras. It means that no element of A annihilates psi, and that states obtained by acting with A on psi are dense in Hilbert space. So, as I say, in the context of quantum field theory, though, psi could be the vacuum, or any state that's any fairly generic state would have this property in quantum field theory. Then there's something called Tomita-Takasaki theory, which was being developed during this period. Well, by Takasaki, obviously, and then by Kahn and others. And there's something called the modular operator of a state in Tomita-Takasaki theory. And let H be what's sometimes called the modular Hamiltonian, minus the log of delta psi. Then what Kahn and Takasaki did purely by hand was to replace the Hilbert space H with with H tensored L2 of R, where L2 of R is the space of square integral functions of a new real variable X. In other words, they added one more operator X, or one more variable X in the definition of the Hilbert space. So they extended the Hilbert space from H to H tensored with L2 of R. And then they added one more generator to the algebra. They took the old algebra and they added not H, not this H, but H plus X as a new generator of the algebra. The symbol with the double prime means to construct the von Neumann algebra generated by these operators. So they took the algebra they really wanted to study and they added one more operator to it. And miraculously, this simple operation of slightly enlarging the Hilbert space and adding one more generator to the algebra turns a type 3 algebra into a type 2 algebra and was useful in studying type 3 algebras. And there's an inverse operation where you can essentially go back from the type 2 algebra to the original type 3 algebra. And so just mathematically, this construction has quite remarkable properties. So the definition made use of a cyclic separating vector, which for quantum field theory, as I said, could be just a vacuum state or any fairly generic state. But although the definition seems to rely heavily on using a particular vector, Kahn showed rather miraculously that the algebra is canonically independent of that choice. So even though it's hard to define this new algebra in a completely canonical way, the new algebra is in fact completely canonical up to a unique isomorphism. And if the original algebra is of type 3 or type 3.1, the usual situation in quantum field theory, then the new algebra is of type 2 infinity. Unfortunately, I told you about a type 2.1 algebra. I didn't quite define type 2 infinity. Maybe I will do it on the blackboard. So in the lecture, I defined B, which was I've defined so far 2 algebras. There's the one you all know about, A, which is type 1. Remember, that's all operators on Hilbert space. Then I also defined the type 2-1 algebra that acts on the infinite set of qubits. So once we have these two algebras, we could take their tensor product. And that's a new type of algebra that's said to be of type 2 infinity. It has a trace because each of the two factors A and B had a trace. But the trace isn't defined for all elements because the trace in the algebra A isn't defined for all elements. And in the two papers, we have learned that B is the right algebra for de Sitter space and C for the black hole. But in the slides I've prepared, I only talk about the black hole. Anyway, this was Kahn and Takasaki. To recapitulate, Kahn and Takasaki discovered that if A is of type 3 acting on Hilbert space H, but you replace H with a slightly bigger Hilbert space, and you add one more generator to the algebra, then miraculously you get, first of all, a type 2 algebra, and secondly, you get a type 2 algebra that doesn't depend on the arbitrary choice you made in constructing it. So the type 2 algebra you make in that way is actually natural. So to get from ordinary, well, okay, with 2020 hindsight, let's try to use the idea of Kahn and Takasaki to explain why entropy is better defined in the presence of gravity. To get from ordinary quantum field theory, where we cannot define the entropy of a region, or we can define it and say it's plus infinity, to gravity, where we can define such an entropy and get a finite answer, we just need to know that gravity adds one variable to the construction of the Hilbert space, namely what I called X, and one generator of the algebra of operators outside the black hole, namely H plus X. Well, to briefly explain why that's true, here I've drawn a Penrose diagram of the maximally extended Schwarzschild black hole in an asymptotically flat space-time. Unfortunately, there isn't time to explain this picture properly if you're not familiar with it. But in brief, if you take the simplest black hole solution of gravity, the Schwarzschild solution, and analytically continue it to extend the space-time as much as possible, you discover that there actually are two regions at spatial infinity, which I'll call A and B. And if you live at this region, then region A is the region outside the horizon, region B is the region behind the horizon. The horizons are these diagonal lines. In this picture, causal signals traveling no faster than light are at an angle to the vertical that's no more than pi/4. So the limit of light trying to escape from the black hole would go out along this null ray. And the gray regions are behind, the gray regions are the, well, this gray region is the region of space-time where you can't avoid ending your life at this singularity. And here's the time-reversed white hole singularity. So the black hole, as discovered by Kruskal, Sakaras, and others, is, following Einstein and Rosen, incidentally, is a wormhole that connects two asymptotically flat universes, which are our two systems A and B. And we're going to look at the picture from the point of view of an observer out here, living outside the black hole. Gravity makes accessible to that observer one more operator above and beyond what you would have in ordinary quantum field theory. That's simply what's called the ADM energy, which in general relativity should be measured at infinity. So the ADM energy measured here at spatial infinity on the right side, I'll call it H right, is the extra operator that's accessible to the observer because of doing gravity rather than ordinary quantum field theory. What I call it X is H left, the ADM energy measured at infinity on the left side. This is a misprint. That right there should be left. For the cyclic separating vector psi, we can take the Hartle-Hawking state of the black hole. That state depends on a choice of temperature, which determines the mass of the black hole we are going to study. The modular operator of this state was determined by Sewell by reinterpreting older and very classical results of these people. The conclusion was that the modular Hamiltonian is beta times h right minus h left. I can write it in this form, that beta h right is h plus beta h left. And setting x equals beta, setting x equals beta h left, we see that gravity is making the operator h plus x accessible to an observer in the right exterior region outside the horizon. So gravity, in other words, has done precisely what Kahn and Takasaki did to simplify their type 3 algebras. It adds one more operator, well, it adds one more variable in the definition of the Hilbert space, namely x. So a quantum state is a function of x as well as whatever it was before. And there's one more operator that acts on the Hilbert space. One more generator of the algebra of operators accessible to the observer, namely h plus x. So following Kahn and Takasaki, the algebra of observables for an observer on the right exterior region is not the type 3 algebra that we'd expect in ordinary quantum field theory, but is the cross product algebra A hat of type 2 infinity. And that gives a framework for understanding black hole entropy. The generalized entropy is just the entropy of the state of the type 2 infinity algebra. There's a similar story for cosmological horizons. That's the topic of the second paper that I mentioned at the beginning. Thank you.
Thanks for the beautiful talk. Are there questions?
The definition of the type 2 algebra, you used an state which depends on the mass of black hole. But at the end of the day, it shouldn't be, it should depend on black hole because this is the system we are working on, but previously you said that it does not depend
You're
on.
correct. So I caught a lot of corners in the explanation, and it was difficult to precisely explain how much is understood and how much not. At the present state, the analysis is when Newton's constant goes to 0, is asymptotically small. If you keep the black hole mass size, the black hole mass is proportional to 1 over Newton's constant, so it's very large. And we allow arbitrary deviations from a starting mass for the black hole, but only by an amount of order 1, not order 1 over g. So the black hole mass in this analysis can change by an arbitrary amount, but an amount that's assumed to be independent of g. I'd like to do better and relax that condition, but for black holes in 4 dimensions, I don't know how to. In a forthcoming paper, Pennington and I, in a simplified model, JT gravity coupled to matter, will define the type 2 infinity algebra in a way that doesn't have this restriction. But I don't know how to do it in general, and I think it's an important point. So good question.
Okay, next we have a question on Zoom.
I was just wondering why there's a requirement for taking qubits and what happens if you don't constrain to only 2 states.
What's the Zoom question?
Do you hear me? Oh, do you hear me?
I completely forgot that it's a speaker. I should have moved this.
Okay, sorry. So the question
I'm
is,
afraid I completely forgot that as a speaker, I should have taken off that mask. This must have been a little funny. I just noticed myself on Zoom. It looked funny.
Do you hear me talking or no?
anyway,
Does it
why
work
is
now?
there a requirement for taking qubits? What happens if you do not constrain to only 2 states?
Well, Murray and von Neumann showed that there's a, if you want an algebra, an infinite algebra where a trace is well defined for all elements of the algebra, it's unique. Well, I'm leaving out some bits. Murray and von Neumann showed that any such algebra that can be approximated by finite dimensional matrix algebras is isomorphic to the one we constructed. So by replacing 2 with some other number, or anything else you can easily think of, you'd get the same algebra up to isomorphism.
Are there any more questions? Yeah, over here.
There's at least one here. Why don't we have a question here first?
I think up there first.
Oh, well,
It's on. Shall I go?
go ahead.
So is it only in backgrounds, gravity backgrounds with horizons that you expect this type 3 going to type 2, or would you also, I mean, those are the cases you mentioned, but do you think this is a more general phenomenon?
Well, if you have access to the whole universe, you would have a type 1 algebra. So the problem only arises because of not having access to the whole universe.
No, I meant semi-classical gravity in, say, flat space. If you were to look at a particular region A and would it be like quantum field theory then?
I'm not sure that singling out a region is well defined in gravity, unless it's the region accessible to an observer.
Okay.
So how would you define it? In quantum field theory, you can arbitrarily pick a region and try to discuss it. But in gravity, because space-time is fluctuating, in order to ask the question, you need to have a natural way to characterize your region. So we should be more specific before trying to answer. I think we will find that most ways to, at least most or maybe all, I'm not sure, ways to characterize a well-defined region in gravity will involve the horizon of somebody. I'm not sure about that. If you have another suggestion, we can discuss it. But we can't just draw a line on a map and say this is our region, because space-time is fluctuating.
Question over here.
So I want to ask, I think if quantum gravity's algebra should be the type 1 because the degree of freedom should be finite. So how do we?
I can't quite hear you. Say it again.
I say the quantum gravity should have a finite degree of freedom. So we should expect the algebra should be type 1.
Mm-hmm.
So how do we expect so in string theory or the conformal field theory?
Well, good question. So I think I'll interpret the question as follows. What I've told you is that if G is 0, we can get a type 3 algebra. And if we work formally in an asymptotic expansion in powers of G, we can see why it would really be type 2. But if G is a positive constant, in some sense, it should be a type 1 algebra. So if we could see that, we would be solving all the puzzles about black holes. So that I can't offer you today. I could only offer you how to get from type 3 to type 2.
There's another
Good question,
question
Bill.
on Zoom.
Yeah, I had a question. So this is related to Rajas's question. If there were a general principle that local algebras and quantum field theory are type 3, and
Okay, in the meantime, we have a
local algebras in type 2 and in the presence of gravity are type 2, the question is, how would that be compatible with holography?
Well, suggest why it might not be compatible, Greg. What do you have in mind?
Well, I mean, there's supposed to be an equivalence
Okay,
in the
sorry.
theory of gravity, and the algebras, the local algebras are supposed to be type 2, and that's supposed to somehow be equivalent to a quantum field theory on the conformal boundary where the local algebras are type 3.
Yeah. So
So
Greg
it
is
seems like there's a tension there.
Greg is asking a very good question, and he's also reminding me that I should have mentioned the work that actually got me started, which was 2 papers by Leutheisser and Liu last year. So first of all, in the context of holography, Newton's constant corresponds to a negative power of an integer called n. For example, in the famous example of 4-dimensional gauge theory, usually G is of order 1 over n squared. So let's discuss it in terms of n rather than G. As Greg is saying, for every finite n, the algebra of observables in the boundary theory is of type 1. That's somewhat similar to what I said in answering a previous question. I said if G is not 0, the algebra is of type 1. That's analogous to n being a definite integer, like 137 or something, just to name a random integer. Now, on the other hand, Liu and Leutheiser showed that if you work asymptotically at n equals infinity, okay, the question arises what kind of large n limit the algebra has. And there might be more than one thing you can do, but Liu and Leutheiser gave an interesting construction where they took the large n limit and showed that although for every finite n you would have a type 1 algebra, the large n limit is actually of type 3. And in a moment, I'll mention something more elementary where that happens. So in the large n limit, they got type 3, but I looked at what happened if you expand around it. And if you work asymptotically near n equals infinity, I showed that the type 3 algebra became type 2. So at n equals infinity, type 3, asymptotically near n equals infinity, type 2. And for finite n, we expect type 1 from holography. So perhaps that answers your question, Greg. But I wanted to, since it might sound a little funny that the type 1 algebra becomes type 3 when n goes to infinity, I wanted to mention something more classical where that happens. This is in statistical mechanics. If you consider a finite ball of gas, the algebra of observables for that system is a type 1 algebra. And that's true for every finite volume. But in the limit of infinite volume, the algebra of observables in quantum statistical mechanics becomes of type 3, as was also understood by people like Araki and his contemporaries in the 60s. And in fact, the thermofield double was introduced by, I think, Haag, Winnick, and Lukenholz. I hope I have the names right. Also in the 60s, because the thermofield double gives a way of studying the infinite volume limit in Hilbert space. But the price you pay is that the algebra of observables that acts in that Hilbert space is of type 3. It's quite similar to what happens in the large n limit in holography.
Okay, question over here.
Maybe I have a stupid question. So supposing I use this type 2 algebra, how can I do some calculation to reproduce the Bekenstein formula?
Well, that's an excellent question. The question is, okay, here I said rather abstractly that there is an entropy you can define for an arbitrary state of the system. But as you say, with gravity, we have formulas starting with Bekenstein for what the entropy is supposed to be. How can you reconcile them? In the original paper and also in the lecture, in the original paper, I didn't understand it. In the lecture, I didn't say anything about that. In the more recent paper on de Sitter space in section 3, we have a calculation that explains that. I should explain it has a limitation. Entropy defined this way has an arbitrary additive constant. It's similar to entropy in classical physics. So we only reproduce the Bekenstein formula up to a constant that's independent of the state. But you will find a clear explanation in the paper doing that in section 3 of the more recent paper.
Question
there? Back to that paper of Leutheiser and Liu, they get a type 3-1 algebra, but they also get a half-sided modular inclusion associated to the horizon. I was wondering if we knew exactly what became of that half-sided modular inclusion when you take the cross product, because it can't really stay, but is there something interesting that can be said about that?
Well, first of all, the reason it tends to go away is that when you add, well, H plus X generates the same outer automorphism of the algebra that H would. So it generates time translations. If you add the generator of time translations to the algebra, since you can move operators backwards and forwards, you can't have the subalgebras they talked about. So naively, it goes away. We wanted to find a way around that in order to account for the generalized second law. We haven't been completely successful. We, meaning Pennington, Chandrasekharan, and me, are writing a third paper, which will have our attempt to grapple with that with middling success.
Thank you.
Because of Aaron Wall's proof of the generalized second law, we feel there's a reason to say more, but we don't know how to do it.
Okay, well, in the absence of further questions, it just remains to thank Ed again for a beautiful talk.